was an ion-induced dipole interaction. The London dispersion forces, on the other hand, are induced dipole interactions. So let's look at two H2 molecules close to each other. No dipole here, no dipole here. But at one instant in time, for a fraction of a second, maybe 10 to the power minus 15 seconds, there is going to be an instance when on this H2 molecule, the electron density is going to be slightly higher on the left-hand side and slightly lower on the right-hand side, just for a fraction of a second. And that is going to instantaneously affect the other molecule, and it's going to affect the other molecule and create a delta minus here and a delta plus here. So this is an instantaneous induced dipole that is inducing another instantaneous induced dipole, and two molecules that do not have a permanent dipole attract each other.
So can you do that again? Just the last part.
Okay. Two molecules that do not have a dipole attract each other because of the instantaneous induced dipole interactions.
How long does the bond last for?
Less than 10 to the power minus 15 seconds. But this is happening so fast that there is a net attractive force. This is the weakest of all the intermolecular forces. And
So these are two molecules that attract each other because of the instantaneous dipole.
this is how the force changes for ions. For dipoles, the force is proportional to 1 over d to the power 4. This is dipole. And for London dispersion forces, it's 1 over d to the power 7. So this is extremely short range. The strength of the London dispersion forces depends on the number of electrons. The more electrons you have, the more instantaneous dipoles you can create, and therefore the stronger the London dispersion forces. The London dispersion forces also depend on the polarizability of atoms and molecules. So look at this. For this instantaneous dipole to create another instantaneous dipole, this electron density must shift very easily. Polarizability is a quantity that measures how the electron distribution around an atom and a molecule can be perturbed. If the electron density around an atom or a molecule can be perturbed very easily, then we say that atom or that molecule has a high polarizability. If the electron density around an atom or a molecule cannot be perturbed easily, we say that the atom or molecule has a low polarizability. So, if you think about electrons that are far away from the nucleus, compared to electrons that are closer to the nucleus, which electrons are going to be more polarizable? The ones that are far away. Okay? So the larger the atom, the larger the molecule, the more polarizable it is going to be. And you can see that in this table, which is not there in the original outline that I posted earlier. So we're going from helium to xenon. We're looking at the boiling point of these noble gases. The only force between these atoms are due to London dispersion forces, because there are no dipoles. So there are only three types of intermolecular forces: dipole-dipole forces, hydrogen bonding, and London dispersion forces. The first two cannot be acting between the atoms for these noble gases. The only thing that is changing is the number of electrons is increasing as we go from helium to xenon, and the polarizability is also increasing as you go from helium to xenon. Both of these contribute to increasing the London dispersion forces and therefore increasing the boiling point.
An iodine molecule has, on average, an electron cloud that is symmetrically spread over each iodine atom. I2 is not polar. The attractions or repulsions between the atoms of I2 molecules can distort their electron clouds. Dipoles can thereby be induced momentarily in neighboring molecules.
Where is the iodine movie? So did you see the iodine? Oh, yeah. No.
The spherical C6...
All right, hold on, it's good. All right. Let's talk about the liquid state and the solid state. The difference between the states is governed mostly by the intermolecular forces. The forces are more strong in the solid state compared to the liquid state. One of the characteristics of a liquid is its viscosity.
The viscosity of a liquid depends on the strength of its intermolecular forces. Glycerol has relatively strong intermolecular forces and is rather viscous. Its resistance to flow is high. Ethanol, by contrast, has weaker intermolecular forces. It flows easily and has low viscosity.
All right. So you've heard the term slow as molasses in January. Never heard that, okay? So if you try to pour syrup in the cold winter, it flows much more slowly compared to during the warm summer. And that's because of viscosity. Viscosity decreases as you increase the temperature. So a high viscosity is a manifestation of strong intermolecular forces. Remember, hydrogen bonding forces are stronger than dipole-dipole forces, which in turn are stronger than London dispersion forces. Okay, another manifestation of intermolecular forces is surface tension.
A paperclip is placed carefully in water, or rather on it. The metal clip floats because it isn't heavy enough to break the water's surface tension. By adding a small amount of soap, we reduce the water's surface tension. The paperclip sinks.
No.
Okay, again, the higher the intermolecular force, the higher the surface tension. Yes?
This is kind of random, but is that like, I don't really remember what happened in this, but is that why like you put pepper on water and you put soap at like leaves or something? Or
I remember that.
yeah.
Okay, I got to think about that.
Okay.
All right. One of the important rules that you will use in organic chemistry is that like dissolves like. Water and methanol will mix with each other very easily because both water and methanol have hydrogen bonding. Okay, that's what I mean by like dissolves like. If the intermolecular forces between molecules is the same for two different compounds, then those two compounds are going to be miscible.
When a gas phase sodium ion enters water, it becomes surrounded by water molecules, or hydrated. The ion-water connection results from ion dipole forces indicated by a dotted line. It is difficult to determine the number of water molecules around a hydrated ion, but 6 is a good estimate for most cations.
All right, the final topic is something that we have talked about previously. Solid state can be broadly classified as either crystalline or amorphous. What does amorphous mean? No long-range order. Okay, crystalline means that there is long-range order. If you know the arrangement in one section of the solid, you know what the arrangement is in another section. We've looked at several types of crystalline solids, ionic solids. Here's an example. Where is it? Okay.
Sodium chloride can be built by first constructing a face-centered unit cell of chloride ions. The smaller sodium ions can then fit into the spaces or holes between chloride ions. Notice that each sodium ion in one of the lattice holes is surrounded by 6 chloride ions at the corners of an octahedron. Therefore, the sodium ions are said to fill octahedral holes.
So that is a type of crystalline solid, that is an ionic solid. There are other types called molecular solids. Let's look at a molecular solid.
The spherical C60 molecule is attracted by induced dipole intermolecular forces to other C60 molecules. The C60 molecules pack together as efficiently as possible, which means that each C60 molecule is surrounded by 6 others in a layer. As successive layers are added, the result is a face-centered cubic arrangement of C60 molecules, with each molecule surrounded by 12 others.
That's buckyball. Okay, we talked about network covalent solids. What is this an image of? Diamond. Okay, let's look at a movie here.
Diamond, an allotrope of carbon, and silicon have the same solid structure. Chemists take advantage of this similarity by making silicon carbide, which combines some of the hardness of diamond with a much lower cost of production.
All right, and we go back here. And the final example is metallic bonding. We've talked about this extensively when we talked about bonding. You have these iron cores. The electron density is delocalized over the entire metal, and this provides for electrical conduction, heat conduction, luster, malleability, ductility. All of these properties are associated with metals because of this delocalized electron band that exists in metals. So we've had, I hope, a fun and stimulating semester, and I hope to see all of you in Chem 3.